Okay, so it is my pleasure to introduce our 55th annual DeLong Lecturer, the second lecture in our 55th annual DeLong Lecture Series. Professor Barry Simon is the Emeritus IBM Professor of Mathematics and Theoretical Physics at CalTech. He has made deep contributions in both mathematics and physics, including work in the fields of analysis, functional analysis, quantum field theory, statistical mechanics, Brownian motion, random matrix theory, non-relativistic quantum mechanics, random and ergodic Schrodinger operators, orthogonal polynomials, and spectral theory. He has over 400 publications, more than 20,000 citations on MathSciNet, and a Google Scholar H-index of 114. He is the co-author with Michael Reed of the foundational 4-volume series, Methods of Modern Mathematical Physics. His 5-volume text, A Comprehensive Course in Analysis, was recently published by the AMS. He has had over 120 co-authors and 30 graduate students. Simon received his BA, summa cum laude, in physics from Harvard University in 1966, and his PhD in physics from Princeton University in 1970. After graduating, he joined the faculty at Princeton as an assistant professor in mathematics and physics and became a full professor by 1976. Simon joined the faculty at CalTech as the Sherman Fairchild Distinguished Visiting Scholar in 1980. He joined the faculty permanently at CalTech in 1981 and became the IBM professor there in 1984. Simon spoke at the International Congress of Mathematicians in 1974 and has given numerous other prestigious lectures in mathematics and physics since then. He is a fellow of the American Physical Society, the American Academy of Arts and Sciences, the American Mathematical Society, and the U.S. National Academy of Sciences. He has served as vice president of the American Mathematical Society and of the International Association of Mathematical Physics. In 2012, he was given the Henri Poincaré Prize by the IMAP. The prize is awarded every 3 years in recognition of outstanding contributions in mathematical physics and accomplishments leading to novel developments in the field. In 2015, Simon was awarded the International János Bolyai Prize of Mathematics by the Hungarian Academy of Sciences. Simon was awarded the 2016 Leroy Steele Prize for Lifetime Achievement by the AMS for his tremendous impact on the education and research of a whole generation of mathematical scientists through significant research achievements, highly influential books, and mentoring of graduate students and postdocs. In 2018, he was awarded the Danny Heinemann Prize for Mathematical Physics by the APS. Before I turn over the mic, let me say a few words about our DeLong series. The lecture series is funded by an endowment given by Professor Ira M. DeLong, who came to the University of Colorado in 1888 at the age of 33. Professor DeLong essentially became the mathematics department by teaching not only the college subjects, but also the preparatory mathematics courses. Professor DeLong was a prominent citizen of the community of Boulder, as well as president of the Mercantile Bank and Trust Company, organizer of the Colorado Education Association, and president of the charter convention that gave Boulder the city manager form of government in 1917. After his death in 1942, it was decided that the bequest he made to the mathematics department would accumulate interest until income became available to fund DeLong prizes for undergraduates and DeLong lectureships to bring outstanding mathematicians to campus each year. The first DeLong lectures were delivered in the 1962-63 academic year. Today, Professor Simon is going to speak about Poncelet's theorem, paraorthogonal polynomials, and the numerical range of truncated GGT matrices.
So first of all, let me thank the organizers of the series for the invitation and for being understanding that I can't come in person because it's still nice to give the lectures. As far as the introduction, I discovered an interesting coincidence 2 days ago. Not only do I have an H index of 114, but so does Elliott Lieb. Anyhow, today I'm talking about Poncelet's theorem and paraorthogonal polynomials, numerical range of compressed GGT matrix. This is joint work with Andrei Martínez-Finkelshtein and Brian Simanek, who are currently both at Baylor. So in 1813, Jean-Victor Poncelet was a prisoner of war. While a prisoner of war, proved a remarkable theorem. He was in Moscow. He went with Napoleon to Moscow. However, I was told because he was not only an officer, but a gentleman, he was actually only under house arrest. So you shouldn't think he was in some dungeon when he found this theorem. And the theorem says the following. Suppose you have a circle with an ellipse inside that happens to have the following strange property. There's a triangle which is inscribed in the circle and circumscribed about the ellipse. So there's some triangle that I can draw, or let me put it differently. You start out and you take a point on the ellipse and you draw the tangent to the ellipse. And it just happens that if you then say, oh, I'll take this point and draw the tangent to the ellipse through this point, and then the tangent through this point, it closes up to a triangle. Suppose there's one such triangle. Then, in fact, there are infinitely many such triangles, indeed so many that their vertices fill the outer circle and the tangent points fill all of the ellipse. That's Poncelet's theorem. There's a huge literature motivated by this gem, which was proved using methods of projective geometry. There's even a whole recent book just on Poncelet's theorem. In this talk, I want to consider three different related developments, three themes. So one involves a theorem that a German algebraic geometer called Jörg Siebeck proved, which was popularized in a later book of Martin, and it says the following. Suppose in the complex plane, you let Wj, where j runs from 1 to b, be the vertices of a convex polygon ordered clockwise. You pick any numbers m, j, and r, and you define, you'll see why I need to do this, WP plus 1, because there isn't a WP plus 1 to be W1. And you define this particular analytic function. So what I'm telling you is you construct a rational function which has poles exactly at the points Wj with positive residues. Then the zeros of M are actually the foci of a curve of class P minus 1, which touches each of the line segments between Wj and Wj plus 1 at the point dividing the line in this ratio Mj and Mj plus 1. I'm not going to tell you what the foci of a general curve is, or what the class number is, and I'm not going to discuss them at all. My point in mentioning this theorem is I want to emphasize there is an n-gon theorem of Poncelet's theorem. If you happen to take P equals 3, then there's always a circle that contains those 3 vertices. And the curve is, in that case, always an ellipse. And the zeros are, in fact, the foci of the usual foci of the ellipse. And so one of the points is that there is a kind of n-gon version of Poncelet's theorem. The second is that this particular function m and its zeros play a special role.
Could I just, there was a question about whether there were slides that go with this, and perhaps you're just giving the introduction, but I just wanted to.
Oh, I didn't share my screen. Oy. There were slides from the very beginning. I am sorry. So let me start at the beginning, but I'll be a little quicker. I'm really sorry. That's terrible. But now I have a problem because, okay.
I should have jumped in earlier. I thought you were giving us a...
No. So he was a prisoner of war. He proved this remarkable theorem. If you have an ellipse with one triangle, there are infinitely many such triangles, and you form this particular rational function given the vertices of a polynomial. said the m's were positive, but in this theorem, they only have to be real, then in fact, the zeros of m are the foci of this curve. The m's do have to be non-zero. And so one of the points is that there's an n-gon version. M and its zeros will play a special role, and these ratios of these m's play a role in the general case. So that's the first theme. Second theme involves certain finite Blaschke products. So starting in 2002, Dape and Gorkin, who happened to be a husband and wife, and along there are probably half a dozen or a dozen papers. Many of them are with collaborators, but the collaborators are different. And all these papers consider finite Blaschke products of the following form. The ZJs are points inside the unit disk. They don't have to be distinct. These are precisely the analytic maps of D to itself, which are analytic in a neighborhood of the closed disk with magnitude 1 on the circle and n zeros. That's not quite true, up to a phase factor. And in their papers, they actually consider ZB and sometimes divide their basic function by Z, but for reasons that will become clear, I prefer to do it this way. Since this function Z times B of Z is by the maximum principle, since it's of magnitude 1 on the boundary of the disk, it's strictly less than 1 inside the unit disk. This map by the Cauchy-Riemann equations is strictly increasing on theta, because the fact that the radial derivative has to point outwards because it's strictly less than 1 inside, Cauchy-Riemann tells you that the angular derivative of the argument has to go in the other direction. So by the argument principle, this map is that there are n plus 1 zeros inside. This map has to grind around n plus 1 times, which means any given point in the boundary, there are going to be n solutions of this equation. They actually, I put a lambda bar here, they put a lambda. You'll see later why I do lambda bar. The main result of this approach is the following. You take any points in D, and any lambda, and form this Blaschke product, and you take any lambda in the boundary of D, and you form this particular function. Then this function has a partial fraction expansion, which has zeros at points Wj inside the unit disk. Sorry, take that all back. This has poles exactly at the solutions of this equation. So these are the Wj's that I defined earlier. They're the solutions of this equation. And the m's are positive and sum up to 1. The fact that they sum up to 1 follows from the easy fact to see that this function looks like 1 over z at infinity. The main issue in this theorem is that the m's defined by this formula happen to be positive, and they did this by finding an explicit formula and saying, oh, look, it's positive. It's left unmentioned that these m's can be thought of as the weights in a probability measure and what the significance of that probability measure is. The following theorem is natural to state in this language. So if you fix two different numbers and you look at the solutions of the corresponding equations, then these W's and U's interlace. Conversely, if you give me any two interlacing sets, there's a unique n-fold Blaschke product. So these are the solutions. This result was actually first proven by Gao and Wu in the SN framework I'm going to discuss below. In their way of thinking about it, the W's and U's enter as vertices of Poncelet n-gons. Their proof was long and involved lots of manipulations of determinants. Dape, Gorkin, and Vos constructed some clever rational Herglotz functions and had a proof that wasn't too bad. We have a simple third proof for reasons that will become obvious later. I call this Wendroff's theorem for Blaschke products. Third theme involves a set of operators called non-unitary contractions of something index 1. We'll see what it is in a second. I forget what I can't read my titles because Zoom puts stuff there. The operator in a Hilbert space is called an operator in a Hilbert space called a contraction. If its norm is at most 1, it's called completely non-unitary if it has no invariant subspace on which it's unitary. In the finite dimensional case, it's not hard to see this is equivalent to there being no eigenvector with eigenvalue of magnitude 1. So we're going to be interested in the finite dimensional case. Completely non-unitary contraction is a contraction all of whose eigenvalues are strictly less than 1. In the finite dimensional case, the defect index of a contraction is defined to be the dimension of the range of 1 minus A star A. So this is a measure of how far A is from preserving norms. If I take the inner product of A star A with a vector phi, I get the norm of phi squared. To say that that has a 0 is to say there are lots of vectors on which this contraction actually preserves norms. And the dimension of the range is defined to be the defect index of this object. It's a sign, it's the codimension of the space on which the operator wants to act like a norm-preserving operator. The space Sn is the set of completely non-unitary contractions on Cn with defect index 1. So they're very close to being norm-preserving, but they're far from being unitary in that all their eigenvalues are less than 1. And these were studied in a series of independent papers by Meerman and by Gao and Wu. Remarkably, they came to it independently. They didn't seem to know about each other, but they both started in 1998. One important theorem was the following. For any set of numbers inside D, they may not be different. There exists an operator A in this space whose eigenvalues, counting algebraic multiplicity, are exactly the ZJs. And secondly, two elements in Sn are unitarily equivalent if and only if they have the same eigenvalue. So they found you could completely describe operators in this space by giving their eigenvalues, and their eigenvalues can be essentially arbitrary. They also studied the numerical range of these operators. Recall that A is an operator in a Hilbert space H. Then the numerical range is the set of expectation values in the physicist's language. Namely, you take the inner product of phi and A phi. This is in my convention where the inner product is linear in this factor. In the usual convention, you put the A on the other side. And we don't run through all vectors of norm at most one. We demand that it only be vectors of norm one. And it's a subtle and somewhat surprising fact that this numerical range is always a convex set. And it's, of course, easy to see it's compact when H is finite dimensional. By the way, the nicest proof of this convexity is since convexity involves pairs of points, you really only have to prove it in the two-dimensional case. And you do a calculation and prove in the two-dimensional case, the numerical range is always an ellipse. And you hear ellipse in 2 dimensions, you should perhaps think of Mr. Poncelet. It's not hard to show that if A is normal, then its numerical range is just the closed convex hull of the spectrum. So in the finite dimensional normal case, N of the numerical range is just the convex hull of the eigenvalues, and so a convex polygon. In particular, if A is a k-dimensional unitary operator with simple spectrum, then N of A is a convex k-gon inscribed in, if it's unitary, inscribed in the boundary of the disk. Standard thing that is heavily studied in various parts of analysis. If you have 2 Hilbert spaces and P is the orthogonal projection, one contained in the other, P is the orthogonal projection onto the smallest space, the orthogonal projection on K. And if A is a bounded operator on A and B is a bounded operator on K, we're often interested in pairs of bounded operators on H and K, so that A is just what you get by putting B, P, B to H. If this holds, one says A is a compression of B and B is a dilation of A. And there's a huge literature on dilations, particularly one's interested in dilations of semigroups, a subject which is not relevant here. And in case the dimension of K is finite, then the difference of the dimensions is called the rank of the dilation. Given any contraction on H, one is interested in finding a K of some larger space and an operator, a unitary operator, which is a dilation of A. So one's often interested in finding unitary dilations of contractions. It's easy to construct such a dilation on the direct sum of H and H. So if you start out with an n-dimensional space, it's easy to get a rank n unitary dilation. But if you start out with an operator on Sn, since it's already close to norm preserving on a space of codimension 1, you can actually prove there's a 1-parameter family of rank 1 unitary dilations. For different lambda, the eigenvalues of this unitary are different, and every point on the circle is an eigenvalue of some lambda. And the big theorem in this paper, in these papers, is if you start out with an operator in Sn, you look at its rank 1 unitary dilations, then for each fixed lambda, n of b lambda is a solid n+1 gon with vertices in the boundary of D. That's not surprising. I already told you they're distinct eigenvalues on the unit circle, and it's a normal operator because it's unitary. Each edge of this polygon is tangent to the numerical range of A at a single point. And as lambda runs through all of the boundary of D, these tangent points trace out the entire boundary, and the numerical range of A is just the intersection of the numerical ranges of the B lambda. You will not be surprised to see that in case n equals 2, this is Poncelet's, a form of Poncelet's theorem. In this case, the rank 1 perturbations are 3-dimensional. the numerical ranges are triangles, and this deals with triangles that are tangent to the ellipse. I already told you that in the two-dimensional case, numerical range of any operator is an ellipse. So this is really a generalization of Poncelet's theorem. Moreover, if one forms this particular object with suitably chosen MJs, then the zeros of M are exactly the eigenvalues of A. Okay, that's the background. The point of the work that I did with Martínez-Finkelshtein and Simanek is that while these authors didn't realize it, they were secretly studying orthogonal polynomials on the unit circle. And I'm going to try to explain, without giving you many proofs at all, what the connection is and how it helps explain all these results. This allows us to find proofs and some extensions and to illuminate the meaning of some formulae. For example, there's this strange formula I wrote down that Dape and Gorkin had. And it's a formula which we'll be able to interpret as a matrix resolvent on this side and a Cramer's rule ratio of determinants on the right. And as I'll explain, this formula is actually a special case of a result called Khrushchev's formula, which he published a year before they found this special case. He did it in the context of orthogonal polynomials on the unit circle. There also, one can go in the opposite direction and find new results in the theory of orthogonal polynomials on the unit circle motivated by these results. So I'm going to give you a very quick, because I assume many people in the audience have never seen orthogonal polynomials in the unit circle, I'm going to try to give you a 10-minute or 15-minute summary. That'll leave me 15 minutes to get a little further, or 20 minutes. I actually call it OPUC on one toe because I wrote these two books on OPUC that were over 1,000 pages. And Michael Eisenman said to me, yeah, I understand it's all this wonderful stuff, but can't you explain it all in 30 pages? And there's a story in the Talmud that I won't go into about explaining something simply. There was explaining the Torah on 1 foot. So I wrote a paper called OPUC on 1 foot. This is not 30 pages. This is an even shorter version. So I called this OPUC on 1 toe. I explained where this came from. So OPUC involves the study of probability measures on the unit disk, which are non-trivial. Non-trivial means not finite point measures. Given such a measure, one can look at the inner product on the unit circle with this measure and form the monic orthogonal polynomials. So you used Graham-Schmidt to essentially successively define the phi n's, and you can normalize them by dividing by the norms and get an orthonormal family of polynomials. These are called OPUC. There's a strange operator, a strange object. You let Pn be the n+1 dimensional space of polynomials in Z of degree at most n, and given a polynomial Pn in the script Pn, you define a new polynomial Pn star by this relation. What this does is it inverts the order of the coefficients and complex conjugates them. And it's a terrible notation, but it was so standard in the literature, I used it in my book. And the reason it's terrible is that the meaning of star depends on what n you're thinking about because of the Zn in front. In particular, if you take the polynomial, which is identical 1, then 1 star is z to the n. So it's an absolutely abominable notation, but I was stuck with it. And Zago found an absolutely remarkable set of recursion relations for orthogonal polynomials on the unit circle. And it's amazing because you can define orthogonal polynomials with respect to any measure of, say, compact support in the complex plane. And it's only in the case of where the measure is on the real axis or on a circle or on things related to it by trivial rotations, etc., for which there aren't recursion relations. In general, there's no recursion relation. There's no simple way of getting a formula like this or the corresponding famous formula, Jacobi formula for the OPRL for the real line case. And what it says is there exist certain complex numbers, alpha n, which happen to be the values of the stars of phi n plus 1, 0. And these are complex numbers which are called Verblunsky coefficients. They're inside the unit disk, and they give you this recursion relation. And there's also an inverse recursion relation that lets you, if you know phi n plus 1, then its 0 tells you what alpha n is. Once you know alpha n, you can, because of this, by this relation, you can compute what phi n is. Once you know phi n, you can compute alpha n minus 1. And so Zago recursion tells you that if you know phi n, you know these first n Verblunsky coefficients. And there's an explicit inverse formula, essentially, because there's a 2x2 matrix here that's invertible. I'm not going to do this calculation because of time, but if you define the rho j's to be 1 minus alpha j squared, remember these are inside the unit disk, so the rhos are 1, you actually discover the norms of the phi n's are the rho j's. Given a probability measure, we define 2 associated functions on D. Carathéodory function, which is this particular strange object, and the Schur function, which is this particular, you'll see they're useful. Schur actually was the first person to realize that these were very useful. And they obey, again, if you have a positive probability measure, capital F has a positive real part because this function has a positive real part. And if you take z equals 0, because it's a probability measure, f of 0 is 1. And the set of such functions are called Carathéodory functions. And essentially, it's a standard fact that it's a version of the Herglotz representation theorem that every function that has these 2 properties is exactly of this form for some probability measure. And this function f, by some little conformal mapping, looking at knowing that capital F has a positive real part, you learn that little f has absolute value strictly less than 1 inside the unit. These are both conditions, by the way, inside the unit disk. They're only being defined on the unit disk. Schur then associated a set of parameters to a Schur function by so gamma 0 is the value, you start out with a Schur function f. you set f of 0 equal to f. The value of f at 0 is called gamma 0. Solving this equation gives you f1. Once you have f1, gamma 1 is given by this. So Schur found this useful iteration. If f is a finite Blaschke product, then after m steps, this gamma m is inside the unit disk, and you can solve this equation. It turns out to go one step further. But if not, in which case f is called the non-trivial Schur function, this process goes on forever, and any Schur function is associated to a sequence of numbers inside the unit disk. And every sequence of numbers inside the unit disk gives you a Schur function. So Schur discovered this strange parameterization of parametrizing Schur functions. And Schur proved the theorem that I just stated, namely there's a one-to-one correspondence between non-trivial Schur functions and sequences of points inside the unit disk given by the map F and its Schur parameters. Verblunsky proved there's a one-to-one correspondence between non-trivial probability measures and sequences alpha n in the disk given by the map. Given the measure, you can go to its orthogonal polynomials and determine the Verblunsky coefficients, and this map happens to be a bijection. You see that, and your eyes light up. Maybe there's a connection, because given any measure, you can form a Schur function, and that's a theorem that Geronimus proved, that if mu is a non-trivial probability measure and f is a Schur function, then the Verblunsky coefficients are the same as the Schur parameters. Absolutely remarkable theorem. And it's for this reason that in the recursion, you could have said, why did I put the complex conjugate on the alpha n? Because if I hadn't, there'd be a complex conjugate here. In 2002, Khrushchev found a new approach to something called Rachmanov's theorem, and he needed to prove the following. Suppose f is a Schur function of some non-trivial probability measure mu on the unit circle. You let fn be its nth iterate. You let bn be the Blaschke product. It may not look like a Blaschke product, but it happens. It's easy to see that these orthogonal polynomials on the unit circle have all their zeros inside the unit circle, and this particular ratio is a Blaschke product up to a phase factor. So you define this to be Bn, and he proved that the Schur function of this probability measure happens to be Fn times Bn. It's a very useful fact. And it's an analog of a result that's used in spectral theory all the time for Schrodinger operators. I think because of time factors, I'm going to skip telling you what Wendroff's theorem is. But I want to tell you what a compressed multiplication operator is. So let's let Pj be the space of polynomials of degree at most j, and let Pn be the projection onto Pn minus 1. I'm calling it Pn because its range is n-dimensional, right? The polynomials of degree n minus 1 is an n-dimensional vector space. Given any non-trivial measure, let's let m of z be multiplication by z. And by a compressed multiplication operator, I mean the usual kind of compression where I take the mz as unitary and I put it between two pn's, and that gives me this compressed multiplication operator when I restrict it to this space. And the following theorem is fairly easy to prove. In OPUC, A depends only, this compressed multiplication operator only depends on the first If two measures have the same first n Verblunsky coefficients, the corresponding a's are the same, they're unitarily equivalent, and their eigenvalues of a are precisely the zeros of phi n, where eigenvalues here means phi n may have a multiple zero, in which case a n has an eigenvalue of higher multiplicity. So in particular, that means the determinant of a minus z is exactly phi n, because I just told you the eigenvalues counting algebraic multiplicity are exactly the zeros of phi n. This is a monic polynomial. This is a monic polynomial. They have the same zeros, so I have this relation. This means if two a's are unitarily equivalent, they have the same phi n, and so by inverse they go recursion, the same alphas. And I tried to sketch the proof, but I'm going to skip that too. Now suppose that I say, yeah, this is all nice, but suppose the measure is a trivial measure. Can I still somehow form some orthogonal polynomials? And yeah, but Gram-Schmidt will stop after a while. The space, if I have a trivial measure with n plus 1 points, pure points, the space is n plus 1 dimensional. After a while, I'll get something when I try to divide to use Gram-Schmidt that has norm 0, but you can form n plus 1 monic orthogonal polynomials. This should have been j equals 0. And the phi n plus 1 that you can still define by Zago gives you something whose zeros are exactly at these pure points. So there's a natural alpha n, but in this case, it isn't inside the unit disk, it's on the circle. And the corresponding multiplication operators are precisely n plus 1 unitaries with a cyclic vector. So this motivates the following. Suppose we're given a non-trivial measure with these Verblunsky coefficients. We form phi n. We pick a lambda in the boundary of D, then one can define what's called a paraorthogonal polynomial by this relation. This is exactly a candidate for one of these things associated with a trivial measure. And the theorem's the following. You fix these, you let A be the corresponding compressed multiplication operator. The paraorthogonal polynomial degree n plus 1 are in one-to-one correspondence with the rank 1 unitary dilations of A. The eigenvalues of the unitary are associated to the zeros of this paraorthogonal polynomial. And so again, we have this determinant relation. The operators A and U act on spaces with natural orthonormal bases. And one can compute matrix elements explicitly, and these are sometimes called GGT matrices after some authors that I won't try to give you the history of. The explicit form is important in some of the proofs, but we don't need it below, so I won't be explicit. I now can summarize our main results. The first is that every compressed multiplication operator lies in Sn. This is almost trivial because our compressed multiplication operators, we start out multiplication by Z preserves the norm. When I compress it, it no longer preserves norm in general, because if I start out with a polynomial of degree n and I multiply by z, I get a polynomial in general of degree n plus 1. And if I project that down, I may kill something. So I'm not going to preserve the norm in general. But if I start out with a polynomial of degree n minus 1 and I multiply by z and I compress it, then I will preserve the norm. So compressed multiplication operators obviously preserve norms on a space of codimension 1, and so their defect index is 1. On the other hand, I already told you that the eigenvalues of the compressed multiplication operator are the zeros of the orthogonal polynomial, all of which lie inside the unit disk. So this is a standard consequence, a consequence of standard OPUC theory. Second theorem, which is highly, which I won't say highly non-trivial, we have two proofs, each of them takes several pages. It's not that hard, but every element in Sn is unitarily equivalent to a compressed multiplication operator. For any set of n elements with multiplicity, there's a compressed multiplication operator with those eigenvalues. Two compressed multiplication operators with the same characteristic polynomial are unitarily equivalent. These theorems, if you go back and look at what I told you with the main theorems classification result on Sn, that's exactly implied by these three theorems. And the third theorem essentially follows from theorem 2 and the fact that I said knowing the zeros determines phi n, and phi n determines the Verblunsky coefficients, and those first Verblunsky coefficients determine uniquely the A up to unitarily equivalent. So that's why you get this unitary equivalence here. Here's what we know about numerical range. You let UL be the associated unitary, W the zeros of phi n cyclically ordered, A to J are the corresponding eigenvectors. That means the A to J's, since they have to be, it has to be true that Z minus WJ of A to J is 0. These have to be the zeros of phi n, and when you multiply this together, you get phi n plus 1, which when you project onto polynomials of degree n with the orthogonal projection gives you 0. So that's why you know these are what the eigenvectors are. You let mj be the weight of A to J and phi n. Then, of course, the fact that this is a normalized vector tells you these weights are 1. And what's true is that the line between Wj and Wj plus 1 intersects the numerical range of A in a single point. And the ratio of the distance from this single point is a ratio of m's. And for each lambda, we know n of u lambda is a solid n plus 1 guard whose sides are tangent to n of A, and n of A is a strictly convex analytic function. This again recovers in terms of this language with explicit information, this theorem that I quoted before on the numerical range. Given these MJs, of course, are exactly the weights. If I look at this U lambda, the MJs are exactly the weights in the spectral measure for U lambda of the vector phi n. So it's natural to form this object, which is the spectral measure for the vector phi n. And our biggest theorem is this theorem here. This is exactly this ratio of Blaschke products. If I divide by phi n, by phi n star, I exactly get what they wrote down. And this is a version of their formula. This is exactly their Blaschke formula. I'm going to skip these other results because of time. Okay, I want to at least say a little bit about proofs before I stop. I figure since I started 5 minutes late, I can go to I was going to say midnight, but whatever, 2 o'clock, I guess, where you are. No, 3 o'clock where you are. So I take a compressed multiplication operator. Oh, this is what I already said. Okay, I'm going to skip this part because I sort of said this. Okay, let's say a little bit about the numerical range. So Pj, the polynomial is of degree at most j. So U lambda acts on Pn and A acts on Pn minus 1. That's how they were defined. A was the projection onto. For any polynomial in phi n, I know that this number is exactly given by this formula. This is just the spectral theorem for the operator U, which is a unitary, a normal operator. And so you can write out in terms of the eigenvalues and these weights. I would like phi to be in, suppose, so the only time this expectation value, the only point on the, right, I have this polygon, I look at the edge of I look at one of the edges of the polygon. The only time that this point lies, the points on this line are exactly the linear combinations of A to J and A to J plus 1. Phi is in Pn minus 1 if and only if this inner product is 0. So the only unit vector that's in this two-dimensional space, that's linear combinations of these two, and in Pn minus 1 is this combination, which you can then compute what the expectation value of A is. You get there's a unique intersection point, and you can compute exactly this distances that I claimed before. Okay, I'm going to skip. You can get the numerical range. I want to skip down to this. I'm going to stop with a proof of this formula. So phi n is the last basis element. Remember this GGT basis. It says take phi 0 up to phi n plus 1, use that as the basis for phi n, and compute the matrices for U and A in this corresponding thing. The U lambda is then a unitary matrix, and the phi n is the last basis element. So the matrix element, this should be phi n, of this resolvent is, by Cramer's rule, a ratio of determinants. On the bottom is the determinant of the big matrix. That's the determinant of Z minus A lambda. And what happens if I drop the last row and column in U? I exactly get back my compressed multiplication operator, because U was a multiplication by Z, and now I've compressing to the n-dimensional polynomials, and that, so we know the numerator is exactly the determinant of Z minus A. But given there's a relation between the determinant of A, which is phi n, and the determinant of U, which is the paraorthogonal polynomial, I exactly get this formula. So this formula is just Cramer's rule. And I think I'm going to stop on this, except for so as I was preparing this talk, so I prepared this talk now probably 3 years ago, but as we were finishing up the paper, I got an announcement of a new book from AMS that has already appeared now, one of these joint AMS-MAA books. And it's called Finding Ellipses. It's by Dipe and Gorkin and 2 co-authors. what Blaschke products, Poncelet theorems, and numerical range know about each other. And their entire book is talking about connections between these ideas of Blaschke products, Poncelet's theorem, numerical range. They forgot about OPUC, which sort of puts it all together in one nice picture. Galkin, by the way, I believe now is an NSF program officer. A rotator in. I think this is her second year in the job. And of course, I end, as all my talks, by mentioning that I have a series of 5 volumes from the AMS: real analysis, basic complex analysis, advanced complex analysis, harmonic analysis, and operative theory. And this is the most recent book. And it's really been a great pleasure to give these lectures, and I appreciate your attention. Thank you.
Well, thank you. I encourage everyone to turn on their mic, and let's thank the speaker.
Stop share.
Let me ask if there are questions.
I have one question about Theorem 6, the giving the basically the Stieltjes transform of this spectral measure as this formula for of this ratio of orthogonal polynomials. It
Correct.
looks like
So, but it's not Stieltjes transform, because it's got this funny, it's got this I forget the name of the kernel now, but it's not got a one. Oh, you know, it is a kind of Stieltjes transform. We usually use Stieltjes transform for real measures, but it's just this. It's what's often called the Cauchy transform that works in
Right.
general. Yes. So
yeah,
what's
so
the question?
I guess that's my question. Do you know if there's any, like, if there already is a version or a hope for a version for Hermitian matrices of getting this for like orthogonal polynomials on the real line, and their actual Stieltjes transform and not the Cauchy transform?
So I thought about this at one point, and I think the answer is no, but it's been several years since I thought about it. See, part of the problem is what's critical for this is when you compress these unitary operators, you get non-unitary operators. If you compress a self-adjoint operator, you still have a self-adjoint operator. So you're not going to have, you don't have this notion of unitary dilations. It isn't at all clear how to make any of that work.
Okay.
So I really think this is one of these things that it makes sense for OPUC, and it doesn't extend to the OPRL case. Part of my company business for the last 20 years has been taking an idea from OPRL and translating it to OPUC or vice versa. But this is one case where I don't think there is such an extension. Of course, if you could find one, it would be very interesting. But
it just seems like
it's not.
Maybe
There are obvious problems with trying to do it.
Yeah, it seems like it would be very, or possibly very useful for random matrices where this Stieltjes transform is.
Oh yeah, you bet. Well, but of course, people do also study CUE.
Right. Yeah, but
so you might be able to use these ideas in the study of CUE.
Yeah, that was
which I haven't thought about.
Second question, if the answer was no or yes. Yeah. Okay, thank you.
Other questions? Okay, well, if there aren't questions now, let's thank the speaker again.
I want to thank the audience.